trig stuff. So my original function, sine mx with parentheses around the mx or without the parentheses around the mx. You will see it both ways. Just get used to seeing it both ways. And so then I'm asking myself, what has a derivative of sine mx? Now in general, the derivative of sine is cosine, so it's going to be a cosine, but we're talking antiderivative. So it's going to be something cosine. Now angles aren't going to change, so it's going to be cosine mx. But if I were to differentiate this right now, remember you can always check everything by differentiating. If I was going to differentiate this, the chain rule would give me a times m. Differentiating, and getting ready to check this. And if I were to check this, just the way it stands now, the chain rule, derivative cosine, would almost give me that sign. We'll worry about that, we'll worry about the almost in a minute. But differentiating cosine almost gives me sine. But then the chain rule would give me times m. I'm not going to want that times m. So to compensate for that times m, I'm going to need a 1 over m. And then back to the almost. The derivative of cosine is negative sine. I don't have a negative here. So to compensate that I don't want that negative here, I'm going to have to put a negative in there. Now let's see if this all checks. And so the derivative of negative 1m cosine mx. So that coefficient just stays there. Then the derivative of cosine is minus sine. The angle doesn't change, but then the chain rule gives me that times m. The two negatives cancel, the m's cancel, and I get sine mx. Didn't leave myself enough room to write it neatly. But it does check. The antiderivative of sine mx will be negative 1 over m cosine mx. Okay, cosine mx. Well, it's going to be a sine. Angles do not change, but then the same thing. If I were just to differentiate this, differentiating just this, sine mx, the derivative of sine mx would be cosine mx, but then the chain rule would give me a times m. I don't want a times m in the answer. I don't want an m out in front here. I just want cosine. And so to get rid of the fact, or to handle the fact that the chain rule would give me a times m, I'm going to put a 1 over m in there. And then that's going to check. The derivative of 1 over m sine mx. Well, that coefficient's just going to stay there. The derivative of sine is cosine. But then the chain rule is going to give me that times m, and we get back to the cosine mx. And so we're starting to see a pattern of the effect of that m, that we are going to divide by it or multiply by its reciprocal. Because if we were differentiating, when I differentiate, the chain rule gives me times m. But now I am anti-differentiating. And when I anti-differentiation, you're doing things backwards. You're doing them in reverse. You're doing the opposite. So in differentiation, the chain rule gives me times m. In anti-differentiation, you're going to get a 1 over m, or divided by m. So the effect of, again, linear arguments, linear. Not x squared, not x cubed, not square root of x. Linear, mx. And even if it was mx plus b, when we have linear arguments here, linear angles, if you will, the effect of that m, when I anti-differentiate, the effect of that slope, when I anti-differentiate, will be to divide by it. And so you just memorize that when I'm doing anti-differentiation and I'm doing my trig, and I have a linear argument, mx plus b, the effect of that slope when I anti-differentiate is going to be dividing by the slope. So 1 over m. then you can just concentrate on what has a derivative of secant tangent. And so you've got to know those derivatives really, really well so we can turn them backwards, because that's all we're doing here. We're just turning our trig derivatives around. So I just ask myself, what has a derivative of secant tangent? And that's secant. And then that is going to check in the exact same way that the first two checked. I'll do one more here. Like I said, we're not going to check all of these. So the 1 over m just stays there. Just a coefficient. Then the derivative of secant is secant tangent. My angle does not change, but when I'm differentiating, the chain rule gives me the times m, then those guys cancel, and I'm back to the original. Next one, secant squared mx. So we have talked about that the effect of that m when I anti-differentiate is to divide by it. So there I've taken care of that m. And again, linear argument here, mx plus b. That's mx squared. Yeah, that's a different issue entirely. So there's the effect of the m. Then I can just concentrate on the secant squared and ask myself, what has a derivative of secant squared? And that's tangent. It would check the exact same way. I'll leave that up to the viewer. Cotangent mx. So the effect of the m is the 1 over m. Now we've got to be really careful with the SIGMs, positive, negative here. I ask myself, what has a derivative of positive cosecant cotangent? Of positive cosecant cotangent, and that's going to be negative cosecant mx. You got to be really, really careful with the positive and negatives. Now, you get them wrong or you lose gobs of points. No, you're going to lose just a point for getting the signs wrong, but be really careful about the signs. What has a derivative of positive cosecant? That's going to have to be negative, or cosecant cotangent. That's going to be negative cosecant. And then lastly, cosecant squared. Again, the effect of the m is a 1 over m. Then I ask myself, what has a derivative of positive cosecant squared? Positive cosecant squared. Well, that's going to be cotangent, but really the derivative of cotangent is negative, and I want to end up with a positive. So to compensate for the negative, I need a negative there. You should memorize the above antiderivatives. But notice it's not 6 new pieces of information. It's 6 old pieces of information that we turned backwards. All we did here was take our derivative statements and turn them around. It's not 6 brand new pieces of information. It's looking at the 6 old pieces of information in a new way. And here I'm just saying what I said before. The derivative of sine mx is m cosine mx. The antiderivative is negative 1 over m cosine x. That what we've said quite, and it's all down here again, what I've said frequently already as we were doing this, that because we're anti-differentiation, the effect of that m is to divide by it. Differentiation chain rule gives us multiplying by that m. Anti-differentiation, we divide by that m. Okay. Next piece of paper. Recall the following derivative formulas. Let's zoom in just a little bit so we see a little better. The derivative of e to the mx is m times e to the mx. The derivative of a to the mx is m a to the mx natural log of a. Derivative of natural log of x is 1 over x. The derivative of sine inverse was 1 over the square root of 1 minus x squared, and the derivative of tan inverse was 1 over 1 plus x squared. So those were all derivatives that we talked about earlier. Now we're going to turn them backwards. And so antiderivative, what is the antiderivative of mx? So the derivative was up here, multiplying by m in the derivative. So when I do the antiderivative, just like when we talked about the trig stuff, the effect of that slope, notice, a linear exponent, there's the word I'm searching for, linear exponent, when I anti-differentiate, the effect of that m will be to divide by it. And so the antiderivative of e to the mx will be 1 over m e to the mx. And notice that is going to check. Now that 1 over m is just a coefficient, e repeats, derivative of the exponent. Remember, those were the words. Repeats, derivative of the exponent. We'll write that up here. Repeats, derivative exponent. So repeats, derivative exponent, and we get back to e to the mx. A to the mx. So there's my differentiation statement over there. Multiplies by m, repeats, multiplies by the natural log of the base. So here, this is going to be 1 over m, 1 over the natural log of the base, doing the opposites. Here was the differentiation statement where I multiplied by the m, multiplied by the natural log of the base. Well, if I'm going to anti-differentiate, do the opposite. The opposite of multiplying is dividing, so 1 over m, 1 over the natural log base, and then I get the a to the mx, and that would check. Now this is the easier one. Derivative of the natural log of x is 1 over x, so the antiderivative of 1 over x is the natural log of x. Depending on how specific the computer is being, they will sometimes slap absolute value around it. Just, you know, if they slap absolute value around it, you slap absolute value around it, because we're not supposed to do logarithms of negatives when we're using real numbers. I'm not going to worry too much about the absolute value. But this one absolutely does check. The derivative of the natural log of x is 1 over x. And then the next one, we'll go out just a little bit. The antiderivative, 1 over the square root of 1 minus x squared, it's just that derivative statement turned exactly around. And so that's going to be sine inverse of x, because that absolutely checks. That's 1 over the square root of 1 minus x squared. And the same thing for the last one. The antiderivative of 1 over 1 plus x squared is tan inverse of x, because that absolutely checks. And again, you need to memorize these. But again, you're not memorizing what there's 5 things here. It's not 5 new pieces of information. It's just your derivatives turned backwards, reversed, whatever. And so you're just learning your derivative statements in a new light. But we do need to memorize all those. Okay, let's end that video.